Okay, now we are going to find the derivatives of some of our other functions. We just did all the functions of this form in the last lesson. We said that if you have x to any power here, that the derivative is simply, you bring the r down, bring the number down, x to the r minus 1. Very cool the way that works out like that. So that's the derivative. And again, don't lose sight. This is the function. This right here, this is a new function which tells you the slope of this function at any point. At any point, this gives you the height of the function. This tells you what the slope is. So, what about the derivative of the sine of x? Well, recall, it's like everything else, the limit as h goes to 0 of the sine of x plus h minus the sine of x, all divided by h. And you look at that and you say, okay, if h goes to 0, you're going to get, if h is actually equal to 0, you get sine of x minus sine of x, which is 0 on top and 0 on the bottom. So we always start off with a 0 over 0 situation. We always have to do something clever in order to find our answer. What did we do with these? We multiplied by conjugates. We what did we do? We multiplied out. We found common denominators, various things. Here's the trick for this one. And if you remember what we did back when we learned our trig, as I said, all the trig you need in calculus you can learn in about a couple hours or an hour or so. One of the things we learned is that if you have the sine of one thing plus another, remember the jingle? Sine, cosine, cosine, sine. Sine, cosine, cosine, sine. So you go sine, cosine, cosine, sine. Then you alternate putting x and h, x and h, and you have a plus right there. So this can all be written like this. Then you have a minus sine of x right there, all divided by h. Well, let's see what we can do with that. Here's what we can do. The sine of x and the sine of x, let's bring both of those together and factor a sine of x out of both this one and this one, and we're going to be left with cosine of h minus 1. Okay, I'll finish this and then we'll look at it together. Okay, now let's check this one out. As h goes to 0, let's do one more line here of algebra. I'm going to write this as the sine of x times the quantity. In fact, I'm going to pull a negative out of this, right? It is negative sine of x times 1 minus cosine of x, all divided by h. That's that one. And then here, I'm going to write this as plus cosine of x times sine of h over h. Right there. Now, do you remember? As, oops, it should have been as h goes to 0. As h goes to 0, remember what the sine of anything is over that thing as this thing goes to 0? The sine of anything over that thing as that thing goes to 0, I'll remind you, goes to 1. So that goes to 1. And this should have been a cosine of h right there. And we also did this limit a couple lessons ago. 1 minus cosine of h over h. We did that one as h goes to 0, and we determined that that goes to 0. So look at our answer. Our final answer is going to be 0 times this, which is 0, plus 1 times this, which is cosine. How cool is that? The derivative of the sine is the cosine. There it is. Let's see if this makes sense. That's a formal proof of that fact. And so I've already proved it to you, but let's see if it's kind of convincing. Here's the sine curve. Looks like that. Here's the cosine curve. Looks like that. What does the derivative tell us? The derivative tells us the slope of this function. Does it look like the slope here is 1? That's what the cosine graph is. Okay, right here at pi over 2. Sure, looks like the slope is 0 there. Sure enough, the cosine is 0 there. So the slope of this graph and the value of this graph are equal. Here it looks like the slope is -1. Sure enough, the cosine is -1 right there. Here the slope is 0 again. Sure enough, the value is 0. And here the slope is back to 1. Sure enough, the cosine is 1. So this graph here tells us the slope of this graph. Very neat. Okay? Well, can you guess about this one? Are you guessing that the derivative of the cosine is the sine? Let's think it through. We've got our picture here. The slope of this one is this one. That's what we're checking. Here the slope is 0. Sure enough, sine is 0 there. Here the slope looks like it's -1. Uh-oh, look at here. Here the value of this one is not -1, but 1. Here the slope is 0 again. Sure enough, this value is 0. Here the slope is 1. Unfortunately, this one is not, the value is not 1, it's -1. And here the slope is 0 again. Sure enough, it's 0. So we're on the right track, except that looks like it's the opposite. Here the slope was -1, and the sine was equal to 1, so we want the derivative of the cosine is the opposite of the sine. Okay? We could actually prove this fact the same way we did the sine, but I like to do it this way just to show you the graph kind of points to what the right answer is, and so that is the right answer right there. So that's those two. Here are the other two I want to do for you. And again, I'm going to do it more like this one than this one. I'm not going to prove these to you. The proofs are kind of involved, but I can give you kind of a convincing argument. Here's the graph of the exponential function, e to the x. And here's what I'd advise you to do it at home here if you want, is to make a table like this. Put down x, e to the x, and the derivative of e to the x. So here's what you do. You choose various points. Let's choose 3, for example. There's 3 right there. Go ahead, get out your calculator, and find what e to the 3 is. E cubed, okay? E cubed, find out what that is. Okay, I'm just going to put a question mark there because I'm not going to go through and actually do it. I don't have a calculator handy, but you find that. And then after you do that, then do this. To get a good approximation for the slope there, you take a point really, really close to 3, like 3.001. That should be fine. 3.001. Take this value, which you already have there. Also find this value. And then find the slope of the secant line. So it's going to be e to the 3.001 minus e cubed. There's the change in the y values, divided by the change in the x values, which is what? This minus this is 0.001. And you find that value, and here's what you'll find. Well, I could have put e cubed in here because this is actually e cubed. You're going to find that this value here is exactly the same as that value. When you find the slope between these 2 points, that value there is exactly the same as this one. So it ends up being whatever this value was. Get your calculator out. This is going to be the same. I'll do it here quickly. Here's e cubed is 20.08. So this one here is 20.08, and this one, if you do all this to it, you'll get very close to the same thing, if not the identical thing. Okay? So that happens at 3. What happens if you put in 5? Well, it turns out that, of course, this is going to be e to the 5th, and if you do the same thing at 5, find the slope of the function right there, you're going to get exactly the same value. If you put in -1, e to the -1, whatever value this is, you find the slope right there by taking 2 points very close together, you're going to end up with exactly the same value. So it turns out, amazingly enough, that the derivative of e to the x is just e to the x. Very unique. In other words, this graph has the property that whatever the height of the function is, the slope is exactly the same. And that's again why e to the x is such a special function. That's why e is so unique and valuable. At 2 to the x or 3 to the x, they don't have that property, but e to the x has the property that at any point, the height of the function is equal to the slope of the function. Very unique. So that's that one. As I say, that's not a formal proof, but I think it's a pretty convincing argument. And there are formal proofs available. Here's the last one I want to do. My marker's running out. I'm going to change it to blue here. A derivative of the ln of x. Well, let's do the same thing. First of all, here's the graph of the ln. It's the inverse of the e to the x. You recall, e to the x look like this. So if you flip it over the line y equal x, here's the graph y equals ln of x. And again, if you do the same thing, here's x, here's the ln of x, and here's the derivative of the ln of x. So choose a point. Choose a point like, again, what did we choose before? I can't remember. Choose 3. So here's the point 3. Stick 3 into your calculator and find whatever the ln of 3 is. And then, again, choose a value close to 3, like 3.001, and do the same thing you did before. These 2 points right there, find the slope of that secant line. So it's going to be the ln of 3.001 minus the ln of 3. That's this y change in the y values, delta y. Okay, what's delta x? Delta x is this minus this, which is this minus this, which is what, 0.001. And if you calculate this, you're going to get something very, very close to 1/3. Okay? If you go on and try it at some other points, here you take, I don't care, 7. You're going to get the ln of 7, and you're going to get 1/7 right there. If you put in 1/5, notice there's no negative values to put here, but if you put in 1/5 down there, notice the slope of that is pretty large. Okay, the slope of that is pretty large. Here's the ln of 1/5. It's a negative number since 1/5 is less than 1. Here's 1 right here. And what's the slope there? You see what it's going to be? 1 over 1/5 is 5. So it turns out that the derivative of the ln of x is just 1 over x, which again, the graph almost suggests that, because look at what happens. As you go out farther and farther and farther, the slope never becomes 0, but it really does level off. So as these become big numbers here, 1 over a big number is a small number, so it's going to level off. It's never going to have an asymptote. It's never going to level off to, it's never going to just have a horizontal asymptote like this. It'll keep climbing up forever, but it's going to just become more and more, less and less of a steepness as you go. And then the opposite here, it goes very, very steep as you get in there towards 0. So as I say, there's no asymptote here, but the slope does get closer and closer to 0 as you go farther and farther out. So there you go. So there's several more functions that are all very important, and we'll go on and start talking about how to use this stuff to actually do some interesting application problems in the next lesson.